Welcome to the ePathshala lecture series in computer science. We are looking at the computer architecture course. So, this module is on exploiting data level parallelism. So, the learning objectives are to discuss about the different techniques that can be used to exploit data level parallelism. So, we are going to look at three different options: vector architectures, SIMD instructions and GPU architectures. So, we have already looked at different types of other parallelism. We have looked at how instruction level parallelism can be exploited. We also looked at how thread level parallelism can be exploited. Now, the third type of parallelism that we are concentrating on is data level parallelism. And when we looked at the Flynn's classification of computer systems, we pointed out that SIMD is one style of architecture where you have a single instruction stream and multiple data streams. You have the single instruction operating on multiple data, particularly important when you look at acting on an array of elements. So, SIMD architectures can exploit significant amount of data level parallelism. Examples are, you have a lot of matrix oriented scientific computing where data level parallelism is exhibited. You also have media oriented image and sound processing where also there is a lot of data level parallelism present. And SIMD is more energy efficient than MIMD because you only have to fetch one instruction per data operation. The same instruction is going to operate on multiple data as against MIMD where you have to have multiple instruction stream and multiple data stream. And SIMD is very attractive for personal mobile devices because you know that mobile devices are very popular for using media applications. So, you have a lot of data level parallelism available there, and SIMD just tries to exploit that data level parallelism. So, we are going to look at three different types of architectures which are exploiting the SIMD type of parallelism, data level parallelism: vector architectures, SIMD extensions and graphics processing units or GPUs. And if you look at the x86 architectures for x86 processors, you can expect that 2 additional cores will come up for per chip every year, and the SIMD width is going to double every 4 years, and the potential speed up from SIMD is going to be twice that from MIMD. So, it is only natural that we will have to explore this type of parallelism further. So, the first architectures that we are going to look at is vector architectures. So, the basic idea behind vector architectures are, say for example, you have a vector operation to do. So, I have a set of elements which form a vector. I have 2 vectors A and B, and suppose if you have to add the 2 vectors, you know the corresponding elements of the 2 vectors are going to be added and it is going to be stored in a third vector. Now, how is this done in a conventional architecture? In a conventional architecture, you know that the first 2 elements are going to be loaded, they are going to be operated on, they are going to be put back into memory, your pointer gets incremented, you get the next set of elements, you do them. So, basically it is executed in a loop. So, that is how a conventional architecture handles a vector addition. Now, when you look at a vector architecture, the architecture itself is entirely different. You talk about vector registers which are capable of storing the entire vector, and you read the data elements into the vector registers. You have instructions which will operate on these registers and which will disperse the results back to memory, and registers are normally controlled by the compiler, and because of the lot of bandwidth that is required, lots of data that has to be transferred between memory and the registers, you need to have techniques which will hide the memory latency, and we also try to leverage the memory bandwidth here. So, the example architecture that we are going to look at is the vMIPS architecture. We have already had a lot of discussion on the MIPS architecture. So, this vMIPS architecture is a vector implementation of the MIPS architecture. It is loosely based on the Cray-1 supercomputer. So, when you look at vector registers, each register holds a 64 bits per element vector. So, earlier our registers, scalar registers are were capable of storing only one 64-bit operand. Now, we have a vector register which is capable of storing 64 such elements. Such is the size of the vector registers. And you also have more number of read and write ports which are supported to the register file. And as far as the vector functional units are concerned, the vector functional units are fully pipelined. So, once the first element enters the functional unit, as it moves down the pipeline, the next element is given to it. So, every element moves through the entire pipeline and finishes operation. So, vector functional units are normally fully pipelined, and data control hazards are automatically detected and handled, and you have vector load store units which are again fully pipelined, and you try to get one word per clock cycle after the initial latency, and you also have support for scalar registers. So, you do not just look at vector registers alone, you have support for scalar registers also. If you look at the VMIPS architecture, we have 32 general purpose registers and 32 floating point registers. And it is not just enough if you just have vector registers and functional units which are which allow you to do vector operations, but you also have to have support in your instruction set architecture. So, you have, these are some examples of VMIPS instructions. You might have a add vector instruction, an add vector to a scalar instruction, a load vector or a store vector. These are some instructions, example instructions for vector architectures. So, to give you an example of how these instructions can be used, we look at our popular DAXP loop where you will have to do an AX plus P. Say the first instruction does a load of a scalar value into some scalar register F naught. The second instruction is a vector load instruction which loads the vector from address pointed to by Rx. So, the first data will be loaded into the first part of your vector register. The second element, the stride length is normally assumed uniform here. So, the next subsequent data will be loaded into the second element space, so on and so forth. So, you are able to load the entire vector from memory into your register V1, and then we do a vector multiply instruction where every component of your vector is multiplied with a scalar value which you have already loaded and available in F naught. The result is written into V2. So, we have done an AX, A is a scalar value, X is your vector, we have done an AX. Similarly, loading vector Y, you load vector Y into another vector register V3, add V2 and V3, so you have done an AX plus Y, the result is put back into memory location. So, this is an example of a DAXP loop which we have already seen with respect to a number of cases earlier. So, if you look at this instruction, you find that in terms of vector instructions, it requires only 6 instructions. If this is going to be implemented on a conventional MIPS architecture, as I already pointed out, this has to come as a loop. The loop has to be executed multiple times. You have the loop maintenance code and all that. So, it will require almost 600 instructions for the MIPS architecture. So, having discussed about the basics of how a vector architecture will look like, we will get into the vector execution time. Vector execution time basically depends on 3 factors: the length of the operand vectors, whether there are any structural hazards available, whether there are any data dependencies available, and the execution time is normally defined in terms of chimes and convoys. And if you look at the MIPS functional unit, we assume that they consume one element per clock cycle. So, the execution time is approximately the vector length, because every clock cycle you have one element finishing to operation. If you ignore the initial latency that is required to fill up the vector, it basically depends on the vector length. So, if you have 64 elements, it is going to take 64 clock cycles. And we define what is called a convoy here. Convoy is a set of vector instructions that could potentially execute together. And a chime is the unit of time that is required to execute one convoy. So, if you have M convoys execute in M chimes, and if you assume a vector length of n and you require M chimes for M convoys, so it basically the entire program requires M into n clock cycles. So, look at an example here. So, you are loading a vector into V1, you are multiplying it with a scalar value, you are loading a vector Y again, you are adding the 2 values and storing it back. This is the example that we already saw. If you look at the try to identify the convoys here and try to calculate the time associated with that, the first load and the multiply instruction can be treated as one convoy. So, this is again you need to pay a little attention to this. So, the load instruction and your multiply instruction is basically dependent. So, the multiply has to take in the value, the scalar value from load. it has to take the value from the loaded element there. But what happens here, which means they cannot be treated as independent operations. But one optimization that is normally done in all vector architectures is the concept of chaining. So, if you have sequences with read after write dependency, as in this case here, they can still be put in the same convoy by using the concept of chaining. So, what you mean by chaining is allowing a vector operation to start as soon as the individual elements of its vector source operand become available. So, you do not have to wait for all the operands to be loaded, as in this case. When you have a load vector, you do not have to wait for all the 64 operands to be loaded. As soon as the first operand becomes available, you can just pass on the first operand to the multiply unit, so that the multiplication will happen on the first element of your vector. As subsequent elements become available through the chaining operation, they will automatically move on to the dependent units. So, that is why we are still able to club the load vector instruction and the multiply vector instruction into one convoy. The second, load and add, it is a similar concept there also. So, load and add can be grouped under one convoy, and the store will have to happen separately. So, there are 3 convoys, you have 3 chimes, and you can see that there are 2 floating point operations per result, which means the cycles for one floating point operation is 1.5, because you take 3 chimes there. And if you look at 64 element vectors, it basically requires 64 into 3, that is 192 clock cycles. The challenges associated with your vector architectures, startup time is one of the issues that we will have to look at, because it initially depends on the latency of the vector functional unit. Only when the pipeline becomes filled up, it starts delivering results at the other end. So, you have to worry about startup time. So, if you assume the same startup times as that of Cray 1, for a floating point add, it takes 6 clock cycles, multiply 7, divide 20 clock cycles, and vector load takes 12 clock cycles. That depends upon the number of unit stages you have in your pipeline. So, if you look at the challenges associated with your other challenges associated with your vector architectures and how you can provide improvements in your vector architectures, how do you make sure that there is more than one element completing per clock cycle? How do you handle non-64 wide vectors? How do you handle conditional execution? How do you optimize your memory to support vector process? How do you handle multi-dimensional matrices and sparse matrices? And how do you program a vector computer? These are some of the challenges that we will have to look at. Getting more than one element to finish per clock cycle depends on whether you have a single lane of execution or multiple lanes of execution. So, when you have multiple lanes of execution as indicated here, if you have 4 lanes of execution, then you can have the elements interleaved, say for example 0, 4, 8 etc. go to the first lane, 1, 5, 9 go to the second lane, so on and so forth. So, all these lanes execute parallelly. So, you will have multiple elements coming out of these lanes parallelly. So, you are able to achieve the execution of more than one element every clock cycle. And handling non-64 wide lengths, if the vector length, even if the vector length is not known at compile time, you can handle the variable lengths using what is called a vector length register. So, the vector length register can be loaded with a variable value, and accordingly the architecture will assume that there are so many elements to be operated on. And when you have vector lengths which are less than the length of the registers, you do not have a problem. If the vector length increases beyond the capacity of the register, you can simply use the concept of strip mining to spread them across the various for registers in multiple iterations. So, this is the example of strip mining that is shown with respect to your strip length registers. The third case is how do you handle conditional execution. Suppose if you have 64 elements stored in a vector register and you have some condition that has been indicated here. For example, if xi is not equal to 0, then you will have to do some operation. So, in which case you will have to check every element, and depending on whether the condition is satisfied or not, you will have to execute a particular operation. Now, this is done with the help of what are called vector mask registers. So, you have a vector mask register where you have a bit for every element of the vector, and depending on whether a mask has been set for that element or not, a particular action will be carried out for that element. So, that is how you can do conditional execution. The other one is how to optimize your memory accesses because you will have to transfer a lot of data from memory when you are looking at vector architectures. So, the memory system must be designed to support the high bandwidth that is required for vector loads and stores. You basically have to spread the access across multiple banks. We have already discussed the concept of banking, and you try to spread the accesses across multiple banks because it will allow us to do parallel accesses. So, you control the bank addresses independently, and this will allow you to do load or store non-sequential words, and it supports multiple vector processes sharing the same memory. The other important concept that is adopted in vector processors is with respect to sparse matrices. So, when you look at sparse matrices, you know all the elements of the matrix are not going to have non-zero elements, and many of them will have 0 elements. So, which means we are interested only in the non-zero elements, and they may be scattered throughout. So, you have a scatter gather operation which is supported, where using the index operation, index of the data where you have a non-zero value, you will be able to gather all these non-zero elements and pack them into one register. So, that is a gather operation. Similarly, after the processing is over, you can just scatter them again using the index values and scatter them to different locations of memory. So, that is the scatter gather operation which is normally supported in all vector architectures. The basic addressing mode that is used is, as you can see, it is just register indirect addressing. And if you look at programmers versus compilers, normally compilers can provide feedback to programmers, and programmers can also provide hints to the compiler so that you get better performance. So, this is an example to show how for various benchmark programs what will happen if the operations executed in vector mode with compiler optimization, what happens to operations executed in vector mode with the programmer's aid, and how much of speed up we have got because of the hints provided by the programmer. So, in certain cases we did not get speed up. For example, if you look at the third entry flow F52 from 91.5 it has reduced to 88.7. So, we are not looking at that case, but in all other cases, most of the cases you find that there is an improvement. So, first case for example 96.1%, it has improved to 97.2%, which means the speed up that you got from hint optimization is 1.52. So, providing a hint by the programmers to compilers may basically aid the compilers in doing a better code generation. So, that is as far as the vector architectures are concerned. So, we know vector architectures are very, very effective for exploiting the data level parallelism. Though they have complicated architectures in terms of registers, the functional units and all of them, they have very good features to exploit the data level parallelism. So, the second way in which data level parallelism can be exploited is SIMD extensions. So, this is a very, very simple case. Our usual processor itself with very little changes that can be brought into the processor like partitioning and adder, you can try to do SIMD extensions. So, the basic concept behind that is, when you look at a 64-bit processor, normally when you look at media operations, you do not find that all operations will have to be done on data which is of the native word size, not on 64-bit operands. Many a times media operations will have to work on say 8-bit operands or 16-bit operands or 32-bit operands. Now, this can be easily done. You anyway have a 64-bit adder, just partition it into 8-bit adders or 16-bit adders or 32-bit adders. So, that is a very, very simple extension that you can do to the existing architectures. But the limitations of such extensions or SIMD extensions compared to your vector architectures is that normally if you are looking at 8-bit operands or 16-bit operands or 32-bit operands, the number of data operands is automatically encoded into your opcode. So, the number of instructions clearly increases very much. There are no sophisticated addressing modes to support your different stride lengths or scatter gather operations like what we discussed earlier. There are no mask registers which are normally supported, which will help you do conditional execution. With such extensions, it makes it harder for the compiler to generate the SIMD code, and it also increases the difficulty of programming in SIMD assembly language. So, if you look at SIMD implementations which are available, the Intel MMX in 1996 itself Intel processors extended their instruction set to support MMX instructions. So you could have 8 8-bit integer operations or 4 16-bit integer operations, and then you had streaming SIMD extensions brought in, then you had advanced vector extensions brought in 2010. So to the existing architecture itself, these changes have been brought in by giving support for some additional instructions and also modifying the architecture slightly. So that is how SIMD extensions can exploit the data level parallelism. So the third case that we are looking at is GPUs, graphics processing units. So as you all know, GPUs are well known for operating on graphics related instructions, which are basically going to work on small types of data. It exhibits a lot of data level parallelism, and GPUs basically try to exploit this data level parallelism. And when you know that GPUs can exploit data level parallelism, can we bring in the GPUs now in order to use this exploitation of data level parallelism? Can we add it to the processor that we already have in order to give better support for data level parallelism? So given the hardware invested to do graphics well, how can we supplement it to improve performance of a wider range of applications? Not just look at graphics applications, try to bring it into mainstream computing. So you have what is called GPU computing, general purpose computing on graphics processing units. So you have a host device which is good for performing sequential operation, and you have a GPU which is going to basically exploit your SMD, data level parallelism, and both of them will work together to give you a lot of improvement in performance. So when you look at graphics processing unit, as I told you, you will have a host and a GPU. So it basically falls under the heterogeneous execution model. The CPU is normally the host and the GPU is the device. People have developed a C-like programming language for GPU. CUDA is one of the most popular programming languages. CUDA is Compute Unified Device Architecture. You also have an OpenCL language which is platform independent. And CUDA, you try to unify all forms of GPU parallelism as a CUDA thread. Your ILP, TLP and your data level parallelism are trying to be exploited when you look at a CUDA thread. And the programming model that is used is a single instruction, multiple thread of execution. So when you look at some of the terminologies that are used, a thread is associated with each data element. Threads are basically organized into blocks. Blocks are organized into a grid, and the GPU hardware handles the thread management. It is not the applications or the OS which handle the thread management. To give you an example of what we mean by the various terminologies here, suppose if you have to multiply two vectors of length 8192, the code that works over all elements is the grid, the complete grid. Thread blocks break this down into manageable sizes, let us say 512 threads per block, and the SMD instruction executes 32 elements at a time. Thus, the grid size is 16 blocks, and the block is analogous to a strip-mined vector loop with vector length of 32. The block is assigned to a multi-threaded SIMD processor by the thread block scheduler. And the current generation GPUs, for example, Fermi, has say about 8 to 16 multi-threaded SIMD processor. So you have threads of SIMD instructions where each thread has its own program counter. A thread scheduler uses scoreboard to dispatch, so you have out of order execution there. There should be no data dependencies between threads, and you keep track of up to 48 threads of SIMD instructions in a typical architecture. You try to hide the memory latency, and the thread block scheduler schedules block to SIMD processors. And within each SIMD processor, you can have say 32 SIMD lanes, and they are wide and shallow compared to your vector processors. In the case of vector processors, you know they are deeply pipelined units, whereas here they are wide and shallow. You have multiple SIMD lanes, but they are also very shallow. So similarities to your vector architecture, if you look at similarities with your vector machines, they work well with data level parallelism problems. Scatter gather transfers are also supported in GPU architectures. You have support for mask registers, you have support for very large register files. But the differences are that The latest GPU processors have shifted to scalar processing. They use multi-threading to hide memory latency. They have many functional units as opposed to a few deeply pipelined functional units that are present in a vector processor. So, why people adopted to scalar processing of late? NVIDIA, which is one of the most popular manufacturers of GPU, NVIDIA engineers analyzed hundreds of shader programs that showed an increasing use of scalar computations and realized that it is hard to efficiently utilize all the processing units within a vector architecture. So, they were not happy with the vector architecture, it was not justified. So, they also estimated that as much as 2x performance improvement can be realized from a scalar architecture that uses 128 scalar processors versus one that uses 32 4-component vector processors based on architectural efficiency of the scalar design. So, starting from G80, NVIDIA has moved on to a scalar processor based design for GPUs. And looking at the memory structures, each SIMD lane has a private section of off-chip DRAM, which is the private memory, which is used to contain your stack frame, spilling of registers and private variables. Each multi-threaded SIMD processor also has a local memory, which is shared by all the SIMD lanes or threads within the block. And the memory that is shared by all SIMD processors is the GPU memory, which the host can read and write. So, again, having looked at the basics of it, so when you write a program, a kernel is a sequence of instructions that can be executed in parallel. A thread is a basic unit of execution that executes a single kernel. A thread block is a collection of threads that execute the same kernel. A grid is a collection of thread blocks that execute the same kernel. And a CUDA program can start many grids, one for each parallel task required. So, if you look at the memory hierarchy, as I already mentioned, you might have a memory per thread, you might have memory per block, and you might have memory which is global to all the grids. So, as a case study, if you look at the Fermi architecture is one of the GPU architectures of NVIDIA. There are also other architectures available, but we will just look at the Fermi architecture. The Fermi architecture has 16 streaming multiprocessors available. You have each SM is vertical, has been shown as a vertical strip that contains an orange portion which is a scheduler and dispatch unit, a green portion which is the execution units, and light blue portion which is the register file and the L1 cache. So, if you look at each of these CUDA cores, a CUDA core has been indicated here. A CUDA core is a simple scalar processor that has a fully pipelined arithmetic logical unit and a floating point unit. It executes a single floating point or integer instruction per clock. It has a very simple instruction pipeline. And Fermi architecture consists of 512 such CUDA cores, as we discussed earlier. And when you look at a streaming multiprocessor is a collection of 32 such CUDA cores that share the same L1 cache. The 32 CUDA cores are further divided into two sets of 16 cores. There are 16 load store units that can access data from the cache or the DRAM, and the 4 special function units that have been indicated execute complex instructions like sine, cosine, reciprocal, square root, etc. So, that has been shown here. So, you have 16 lanes, 32 CUDA cores divided into 2 lanes of 16 each. You have the special function units and the LSUs that have been indicated. And you have a thread scheduler. So, Fermi supports a 2-level scheduler. At the chip level, you have a global scheduler which schedules thread blocks to the various streaming multiprocessors, while at the SM level, you have a warp. A warp is normally consisting of 32 threads. So, a warp scheduler distributes warps of 32 threads to its execution units. And when you look at concurrent kernel execution, Fermi supports concurrent kernel execution where different kernels of the same application context can execute on the GPU at the same time. And concurrent kernel execution allows programs that execute a number of small kernels to utilize the whole GPU. And you also have a dual warp scheduler because you have dual lanes. The SM schedules threads in groups of 16 parallel threads called warps, and each SM features two warp schedulers and 2 instruction dispatch units, allowing 2 warps to be issued and executed continuously. Concurrently. Fermi's dual warp scheduler selects 2 warps and issues 1 instruction from each warp to a group of 16 cores, 16 load store units or 4 special function units. And if you look at the PTX ISA, which is supported in your NVIDIA architectures, PTX is a low-level virtual machine and ISA designed to support the operations of a parallel thread processor. So, at program install time, PTS instructions are translated to machine instructions by the GPU driver that has been installed. And if you look at the memory hierarchy, as I have already pointed out, you have some memory which is common to the thread, some memory which is common to a group of threads, and some memory which is common to the entire grid. So, this is with respect to your Fermi architecture. And as far as the hardware mapping is concerned, as far as the CUDA programming model is concerned, the programming model which involves threads, thread blocks and grids, they map directly to the Fermi hardware architecture involving CUDA cores, streaming multiprocessors and the whole GPU. This is the mapping that is done. So, a thread is mapped onto the hardware model where it executes in a CUDA core. The SM dual warp scheduler schedules a collection of threads in every core. Thread block executes in an SM. The global scheduler allocates a thread block to SM. A grid executes in a GPU itself. A per thread private memory is 1K registers per core. Per thread block shared memory is configurable L1 cache, and per application the global memory is L2 and the DRAM. So, this is how a typical GPU's architecture is. So, and you also have other innovations with respect to your Fermi architecture like fast double precision operation, caches for GPU memory, 64-bit addressing and unified address space, error correcting codes, faster context switching, faster atomic instructions. So, to summarize, we have seen how data level parallelism can be exploited by 3 different styles of architectures: vector architectures, SIMD style of architectures or SIMD extensions, and GPUs. We have also looked at the differences and similarities between the various types of architectures. Vector architectures support vector registers, vector instructions, deeply pipelined functional units and pipelined memory access. Special features like conditional execution, varying length of vectors, scatter gather operations, chaining etc. are supported in vector architectures. And when you look at SIMD extensions, they basically exploit the data level parallelism with minimal changes, and they are very useful for streaming applications. And GPUs try to exploit all types of parallelism. They are an example of a heterogeneous architecture. They have SIMD lanes with multi-threaded execution, and there is a memory hierarchy for efficient access of data. There is support for PTX low level virtual machines, and we have looked at Fermi architecture as a case study. Thank you.